First up, heating curves. So potential energy is stored energy. So potential energy in substances changes when the temperature is constant. On the flip side, kinetic energy or energy of motion changes when the temperature changes. Now this should make sense. Why? Well, temperature is a measure of the average kinetic energy. So if temperature is changing, kinetic energy is changing. So that means when the temperature is constant, kinetic energy is constant. So that must mean the kind of energy that's changing is potential. Some other things to know, when melting, the solid and liquid phases are in equilibrium. And fusion is melting. So there's an equilibrium, a balance between the solid and the liquid phases at the same temperature at the melting point. We could also call it the freezing point. They're at equilibrium. So the heat of fusion is the amount of heat that we need to change 1 gram of a solid to a liquid with no change in temperature. Okay. Now, when melting, the solid and liquid phases again are in equilibrium. The heat of vaporization is the amount of heat needed to change 1 gram of a liquid to a gas with no change in temperature. It's going to be at its boiling point. Now, when boiling, the gas and the liquid phases are in equilibrium. Remember those values for water that were found in Table B? Yeah, they apply here. Right? So when we're going from Kelvin to Celsius, we're going to subtract 273. And when we're going from Celsius to Kelvin, we're going to add 273. So remember, this formula is found in your reference table. Now, a heating curve is endothermic. There's energy being absorbed. So how can we tell at a quick glance? Well, the curve goes off. That's real simple. Okay, so what happens here is we have water being heated as a solid, then it melts. Then the liquid is heated, then it boils, then the gas is heated. That's the flow of a heating curve. Now, in a question, you could only be shown a section. Well, you would have to be given some more information, like it started as a liquid, okay, in order to determine which part of the graph you're being shown. So when I look at a heating curve, we have a solid, and we have solid to liquid, it's melting, a liquid only, liquid to gas, it's boiling, and then gas only. So solid only, this, we have solid and liquid at equilibrium. Here we have liquid and gas at equilibrium. Here the temperature is constant. Here the temperature is constant. And here the temperature is changing, right? You can see that in each section. What we can also find is the melting point and boiling point. So we find the flat line where it's melting and we go across and read it off there. That would be the melting point. Then we find the flat line where it's boiling and go across and read the temperature, and that's the boiling point. This line is representative of the heat of fusion. This line is representative of the heat of vaporization. So we can see that the heat of vaporization is bigger. Why? Because this should make sense. It takes more energy to go from a liquid to a gas to boil than it does to melt. So the line for the heat of vaporization is going to be longer because it takes more energy to go from a liquid to a gas than it does to go from a solid to a liquid. All right, now temperature is average kinetic energy, right? So when the temperature is changing, kinetic energy is changing. And in this case, in every place where the kinetic energy is changing, it goes up because it's a heating curve, the line is going up. And if the temperature is constant, the kinetic energy is constant. So those are where the lines are flat during a phase change. Now, the other kind of energy that could be asked about is potential energy. So if the temperature is changing, kinetic is changing. So that means potential must be constant. So in those places where kinetic is changing, I know potential is constant. And if the temperature is constant, so kinetic energy is constant, then potential energy is changing. And because it's a heating curve, it's going up. Okay. So here's just a representation of what is occurring. You can see again, like we talked about already, that the heat of vaporization is larger than the heat of fusion, right? All right, so we're going to go step by step through the questions that you need to answer in your notes about heating curves. So first it says label the states of matter. Do you know how to do that? Again, it's going from solid to liquid, and then liquid to gas on that whole straight line there. Next, label where the potential energy changes. Well, that changes when kinetic is not, right? So the potential energy is going up here and here. Label the lines where kinetic energy is changing. Kinetic changes with temperature, right? So it's changing here and here. Now label the melting points and boiling points. So going across from that line, that would be the melting point, and going across from that line, that would be the boiling point. Label the heat of fusion and the heat of vaporization. Heat of fusion is represented by this line, and the heat of vaporization is represented by that line. Now add a line to show what will happen if vaporization completes and the gas is heated. Well, it would do this, right? Then that would be where the gas is. A couple of extra questions. At what point does the substance begin melting? Yeah, B. At what point does it stop melting? C. At what point does the substance begin to vaporize? D, right? And then we aren't sure because it doesn't necessarily look complete, so we can't really say when the substance finishes vaporizing. Now, is this a heating curve for water? Well, no. How do I know? The melting point of water is 0 degrees Celsius or 273 Kelvin, and that is not the temperatures that are here, okay? All right, now let's cover cooling curves. Again, we're going to have potential energy changing when the temperature is constant. Again, we're going to have kinetic energy changing when the temperature is changing, because still temperature is a measure of the average kinetic energy of the particles. Fusion is still referred to as melting. Now, a term that you might see is the heat of solidification. So opposite of the heat of fusion, it just means going from a liquid to a solid, becoming a solid. Still, when melting, solid and liquid are in equilibrium, but also when freezing. And then opposite of the heat of vaporization is the heat of condensation. So when the gas is becoming a liquid, and when boiling or condensing, the gas and the liquid phases are in equilibrium. Still remember that the values for water are found in table B. Now we may have to do joule to kilojoule conversions. Okay, so 1 kilojoule is 1,000 joules. So if I have a number in kilojoules, I multiply it by 1,000. If I have a number in kilojoules, I multiply it by 1,000. So what do you get for the next one? Yeah, this one. Now, if I have a number in joules already and I want to convert it to kilojoules, I divide by 1,000. So I would get this. So what would you get for the next one when you convert those joules into kilojoules? Yeah, 347. Now, a cooling curve is exothermic. Energy is being released. So It looks very similar to a heating curve, except it's going in the other direction. It's going down. So we start with a gas to liquid or condensing, liquid cools, liquid to solid, it freezes, and then the solid cools. So again, you can see the gas is cooled, it condenses. The liquid is cooled, it freezes. The solid is cooled. All right, and the heat of fusion or the heat of freezing or the heat of solidification would represent it on that line, and the heat of vaporization or the heat of condensation would be represented by that line. And again, temperature is average kinetic energy, so when temperature is changing, kinetic changes. Now this time, because it's a cooling curve, wherever the temperature is changing, the kinetic energy goes down. And then if the temperature is constant, the kinetic is constant. So that would be in those two spaces. Same idea for potential energy, right? So if the temperature is changing, the kinetic is changing. So the potential is constant. So anytime the kinetic changes, the potential is constant. And then if the temperature is constant, the potential would be changing. And since it's a cooling curve, it is decreasing in those two spots. All right, so here is another example. You can see the cooling curve happening. Gas, condensing, liquid, freezing, solid. Here's what's happening on a molecular basis or on a particle basis. You can see the progression from gas to solid. And here's another representation where you can see here's where condensing begins, condensing ends. Freezing begins, freezing ends. Okay? Now, you have some graphs in your notes. Let's go over what you should include. Labeling the states of matter. Gas, gas to liquid, liquid, liquid to solid, and solid. Label the lines where the potential energy changes. Since it's a cooling curve, remember, potential is going to be going down. And it's changing when the kinetic is constant. So in those spaces where the kinetic is constant, potential goes down. Where does the kinetic energy change? Where the temperature changes. That's like the easiest one to identify, right? Label the condensing and freezing points. So the freezing point where the line is flat, the condensing point where the line is flat. Label the heat of fusion and the heat of vaporization. Heat of fusion would be where freezing occurs, and the heat of vaporization would be where condensing occurs. At what point does the substance begin freezing? Yeah, D. When does it end freezing? Yeah, E. At what point does the substance begin condensing? Yeah, B. Where would it end condensing? C. Is this a cooling curve for water? Nope, no. Why not? The freezing or melting point of water is 0 degrees Celsius and 273 Kelvin. And here it's 100 degrees Celsius. That is way too high.